Hi, folks. We now will finish up Chapter 8 by talking about doing hypothesis testing for claims about standard deviations or variance for a population. Okay, so the big thing to focus on is the chi-square. That's what we're going to be using. That's the distribution that is appropriate for testing claims about variances and standard deviations. Here's the cast of characters. N is the sample size. S is the sample standard deviation. S squared sample variance. Sigma is the claimed value of the population standard deviation. And sigma squared is the population variance claimed value. All right, you probably already knew that, but sometimes it's good to review. Requirements is that we need a simple random sample, and that we have gotten a sample from a normally distributed population. Now, note here that we, can be somewhat casual in the other sort of hypothesis tests, but when we're testing claims about the variance or standard deviation, and we're going to use a chi-square distribution, we need to really make sure that we have a sample that is convincingly normal. Because if it's not, then we're going to have to use some non-parametric testing, okay, which is later on in the course. This is the test statistic that is used. You probably have already seen this from when we were doing confidence intervals. Chi-square is a random variable. Here's the calculation. N minus 1, n is the sample size. N minus 1 times the sample variance divided by the hypothesized population variance. So there's only 3 numbers that go into this calculation. We calculate p-values and critical values just like we have before, except we will be using a chi-square table. Let me show you. In your textbook, this is a an extract of it. Table A-4 is your chi-square distribution table. This will give you critical values. Down the left-hand column, like all these tables have, is going to be your degrees of freedom. And across the top, you'll have areas to the right, not to the left, but to the right of the critical value. And that's different from the Z table, which is for areas to the left. Okay? I'll show you how to use technology to calculate your p-values. Don't worry about using the table to calculate your p-values. That's too much, and it doesn't give you a good result. Most of you have graphing calculators, so go ahead and use your p-value. So you could either use p-values or critical values. Regardless, n minus 1 is the degrees of freedom that you'll use for your chi-square distribution. We're going to remind you that the chi-square test of this section is not robust against a departure from normality. That's why you want to check it. Probably want to use a QQ plot, also known as a normal quantile plot. And what it means for a test to not be robust, that means that the test does not work well if the population has a distribution that is not close to being normal. Okay? Properties of the chi-square distribution. I think we've seen this before when we were doing the confidence intervals for variances or standard deviations. So I'll let you look at that and then move on. We've already seen this picture before. Chi-square distributions are skewed. The random variable is never going to be negative, always 0 or positive. And that the peak is going to be directly over the number of degrees of freedom. And the larger the degrees of freedom, the further to the right the peak is. And the shorter the peak is going to be, the more spread out the distribution is going to be. Now we're going to do one example to show you what this looks like And this is going to actually be a one-tailed test. Listed below are heights in terms of inches for a simple random sample of 10 supermodels. So here are 9 measurements of heights of supermodel women. We're going to consider this claim that someone has made that supermodels have heights that have much less variation than the heights of women in the general population. When we think about supermodels and their figures, they are typically going to be tall and skinny with not a whole lot of variation. So we're going to test this notion, this idea that there's a lot less variability in the heights of women who are supermodels compared to the general population of women. We're going to be using an alpha level of 0.01 in this instance. Okay, no problem. And we're going to test the claim that supermodels have heights with a standard deviation that is less than 2.6, because 2.6 inches is the standard deviation for the heights of women in general. Now, we've got this set of 10 heights right here. This is our data set here, our sample. Calculate the mean and standard deviation. Well, we don't care about the mean, but the standard deviation is 0.8942816. You square it, you get the variance of 0.7997395. Okay. I'm assuming that you know how to calculate variance and standard deviation. Now, before we go any further, let's check our requirements. Do we have a simple random sample? Well, we were told that we do, so check. Number 2, did we sample from a normally distributed population? Well, we do a normal quantile plot. Hey, this looks good enough for me. These numbers are somewhat a little bit random above and below the line, so good enough. Now, our null hypothesis, we're going to state that the standard deviation for the heights of the supermodels is equal to 2.6. Remember, the null hypothesis always has to be a statement in the form of an equation for the parameter. In this case, the parameter is the standard deviation for the population. So we're going to set that equal to 2.6, but we want to test the claim that there's less variability. So our alternative will be that the standard deviation is less than 2.6. So this is going to be a left tail test, a left tail as in a one tail test. Level of significance is 0.01 for alpha. All right, we're using the chi-square test statistic. Remember, the sample size was 10, so we have 10 minus 1 for n minus 1. S squared, that's the sample variance. Now let's double check that. That doesn't look right here. Oh yeah, so S squared is 0.79973995. So that's actually what we should have here. Don't square it. This is a typo here. This is just going to be 0.79973995 without the squaring. Now, if we wanted to square it, we would do 0.89421 or 42816 squared. Okay, so sorry about that. But this is the sample variance that goes up here, divided by 2.6. And that would work out to a chi-square value of 0.852 with 9 degrees of freedom. Now we're going to go with this test statistic value of 0.852. May or may not be right. Now let's go ahead and get our critical value. You don't need to know the test statistic value in order to get the critical value. So I'm going to get out of this, go to my chi-square table. Here's my chi-square table, table A-4. I'm going to go down the left column down to 9 degrees of freedom that you see right here. And if we want alpha to be equal to 0.01 in the left tail, that means that we want an area of 0.99 to the right of that critical value. So that's why we're going to come down the second column down to 9 degrees of freedom, and you have 2.088. So 2.088 will be your critical value. Notice that your test statistic, 0.852, is going to be less than that critical value. It's more extreme. Further away from the mean. The mean is going to be 9 because the chi-square distribution has a mean that's equal to its degrees of freedom. So your test statistic value is more extreme than the critical value. It's at least as extreme as the critical value. So that means we would actually reject the null hypothesis. And because the null hypothesis is that the population standard deviation is equal to 2.6, we will reject that and then conclude that the alternative must be true. And the alternative was that the standard deviation was less than 2.6, which is meaning the amount of variability in the heights of the supermodels is less than that of the general population of women. Yay! So we use critical value to make that decision. Now, what if you wanted to use your calculator? If you go into your statistics menu of your TI-84, you'll see an option to do a sigma test, okay? But what I'm going to show you on the graphing calculator is how to calculate this p-value here. Okay, so I need to know what is our test statistic values, 0.852. I'm going to pull out my graphing calculator here. So we're going to go into our distribution menu, and we're going to go down to option 8. And the first value that you're going to put in is negative infinity. So there's negative 1 times 10 to the 99th power that should be a negative negative 1 times 10 to the 99th power. Alright, okay, moving along here, comma. Then the right endpoint would be your test statistic value. We want to find this area that's under the curve between negative infinity and your test statistic value of 0.852. So between negative infinity and 0.852. So we will put 0.852 as your second point, comma. Your third point will be the number of degrees of freedom. So it has the same syntax as for your TCDF. Close parentheses, hit enter. And notice it gives you a value of about 2.9 times 10 to the negative 4th power, which is a really small value. And it's much smaller than alpha. Remember, alpha was 0.01. Because our p-value is much smaller than alpha, we would reject the null hypothesis and come to the same conclusion as we did for the critical value, in that there is enough evidence to support the claim that there's less variability in the heights of supermodels compared to the heights of women in general. Now, if we had already calculated a confidence interval, suppose that we did a 98% confidence interval using the methods of 7-4. This is what the confidence interval would look like for the standard deviation. I'll let you check the details on your own because we've already had this discussion. And it turns out that this confidence interval is between 0.5 and 1.7. And notice that our hypothesized value for sigma was 2.6 inches. That's outside of this confidence interval. And when your hypothesized value for your parameters lies outside the confidence interval, then you would reject the null hypothesis. Okay, so with that said, we are done with this section and we're done with chapter 8. Now, you won't see any more videos posted until I get back from vacation next week, okay? So we'll see you after I get back, okay? Talk with you next time. Goodbye.